Hello and welcome back to the lab. In today's episode, we finished work on the HP 3314A function generator. You can tell I finished work because it's actually sitting right here operating right now. Um, there were a lot of twists and turns during this repair, including we experienced a hurricane and we lost power and part of my tree fell down and my rear fence and all kinds of fun stuff like that. But we made it through the hurricane and everybody is safe and sound. Um, at the end of this video, we're going to do the now infamous, Easter egg. So you're going to want to see that. So stick around and watch the whole video. And don't forget to click like and subscribe. So let's get started on today's video. Okay, so when we left off, we had found a shorted capacitor. This particular cap was no longer capaciting. It was now a wire. So this electrolytic was pulling down the negative 15 volt rail, this 470 microfarad, and I replaced it with what I had on hand, which was 100 microfarad temporarily while I ordered the correct replacements. So the replacement capacitors have come in. They were delivered actually in the middle of a hurricane when I had no power or internet or any way to do any replacement of them. But the power has since been restored. Um, these high quality capacitors are about $4 each, I think, um, instead of those 10-cent ones that we like to play with. Don't put those things in your equipment. They're fun to play with, but they're no fun to repair this vintage stuff with. Sprague. Don't be vague. Ask for Sprague. It's the good stuff. Now, I'm going to replace the 100 microfarad with the correct 470. I decided to also put one on its mate on the positive 15 volt rail, just because they're the same and higher probability that this one will fail once we found that this one has already shorted out. Um, so we're going to get rid of both of those. So what I use is the old trusty, dusty Weller WP30 with the turquoise handle, and this bad boy right here. Simple tools, but very effective. I've been using the same tools since the 70s, and that's how I do my component replacement for these through-hole uh, components. Notice the solder I'm using, Radio Shack 6040 solder. It's probably 25 years old. Also, I'm still using it. There's quite a bit left on that roll, so I might as well keep going with it. All right, let me get these capacitors replaced, and we'll come back once I get this board installed back in the instrument. Now, if you recall, this will not solve the problem. It will bring the power supplies back up, but we still have a problem where it will not boot up. So probably something wrong in the processor, the microprocessor, or the controller circuitry. So we got some more troubleshooting to do. But let's get these caps changed out and get this board back in the instrument. We'll be back when that's accomplished. Okay, so the board is back inside the instrument. Let's go ahead and plug it in and turn it on and measure the negative 15 volts and see if we have negative 15 volts across that capacitor. Negative 14.98, that sounds like 15. And the positive 15 volts, we have plus 14.95. That sounds like plus 15. All right, close enough. All right, very good. So the power supplies are back up and with the correct capacitors in there. Now, we still have no display. Still doing the same thing it was doing last week. Counts down from 999 to 000 and then just goes blank. I think we have a problem somewhere in the CPU board on the 6800 board. So let's flip it over and take a look at some of that and see if we can find something going on there. Okay, so I'd like to start by taking a look at the reset pulse on the reset circuitry. See if we have basic system clocks and and that sort of thing. So we'll see if we have those preliminary signals. Um, we have the 4 megahertz. Let's zoom in a little bit. We have the 4 megahertz crystal oscillator here. Goes through some circuitry to buffer it, and a NAND gate that's used as a buffer also. We should have 4 megahertz at the output of that NAND gate, U222 pin 3. All right, so we'll take a look for that. We have a divide by 2 flip-flop here, so we should have 2 megahertz here. Another divide by 2 flip-flop, we should have 1 megahertz over here. Goes through some delay timing circuitry. Yeah, so we should have 1 megahertz over here on TP5. So we'll take a look at TP5 first, and if we have 1 megahertz there, it means everything up to that point is working properly. We also have TP4, which is it's also 1 megahertz. I guess it's a different phase. So we'll take another look for the 1 megahertz on TP4, and then we can assume all of that circuitry is working properly. U205, I believe, is a divide by 10. So it takes 1 megahertz input, 100 kilohertz output. Yes. So we'll take a look over here and see if on pin 9 and also pin 8 we have the 100 kilohertz. Divide by 10 from the 1 megahertz and make sure that signal is correct. Actually, we should look at all of these outputs all the way down to make sure all of those signals are correct. So I'll take a look at all of those with the scope and see if all of that stuff is correct. And if we have all of those signals properly, then I think everything on this page is functioning properly. Okay, so I set the camera up to look at the analog scope, and we're going to probe some of those test points. This is TP4. That's 1 megahertz. It absolutely is. Here we go on TP5. That is 1 megahertz as well. Very good. I wanted to look at the reset line. Let me see what that is. That reset is U203 pin 4. U203 is over here in the corner, pin 4. Gotta remove my ground lead on my scope probe because it doesn't reach. Come on. All right, 1, 2, 3, pin 4. It's flickering, but it's staying high. Does it go low? Let's turn up the intensity a little bit. Well, that's a funny looking signal, but it's essentially logic 1 all the time. Let me turn power off and back on again. It does go down and then back up. Yes, indeed it does go down and back up. We have a little bit of something fun going on there. I'm not sure what that is, but it seems like it's a logic high, so I guess it's okay. All right, and I wanted to look at the 100 kilohertz U205 pin 9. U205 is, well, I don't see it. Where's U205? All right, well, I'm going to have to pause the camera. Oh, there it is. There's U205, pin 9. Okay, so 1, 2, 3. U205, pin 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9. 9 should be here. That should be 100 kilohertz waveform. It is 100 kilohertz waveform, so that one is correct as well. It looks like essentially all our clocks and our reset pulses are working properly. So we'll have to take a look elsewhere. Let's take a look more directly at the CPU. So I've been probing around on the controller board, and I wanted to show you on the schematic what I've been looking at and show you what I found so far. Here we see the Motorola 6800 microprocessor chip, and it has this chip has 8-bit data bus and a 16-bit address bus. Okay, when I take a look at the address bus, what we see is at A0, we see a 500 kilohertz square wave, a square wave with a period of 2 microseconds. A1 is a period of 4 microseconds. A2 is a period of 8 microseconds. A3, a period of 16 microseconds, and so on, all the way up through A15. So basically, it's incrementing. Every clock cycle, it increments by 1. So it's going through all 64,000 or all 2 to the 16th addresses one at a time, incrementing as it goes along. That's what a CPU would normally do unless it's instructed to do something different. So I'm guessing that this is probably working normally. Here we see this is simply a buffer chip that can either be enabled in normal mode or disabled in test mode with this little jumper over here. Okay, so in normal mode, it's simply a buffer and it passes through whatever's on the address bus of the CPU out to this, what they call this A prime address bus that goes to the rest of the processor circuitry, including all the ROMs and all the RAMs, anything that needs an address to be addressed. Okay, and what we see there is the same thing that's on this A address bus. The same thing appears on the A prime address bus. That means the data is being passed through. The addresses are being passed through from this side of the chip directly to this side of the chip. So these two chips are working properly. Now, on the data side of the CPU, the data bus, D0 through D7, when I look at these pins, they are showing some sort of data. I'm talking about looking at them with my analog oscilloscope, right? They're showing some sort of data. They're toggling between logic 0 and logic 1 at some sort of predetermined state, but they are all moving. And I think there's probably something that seems correct is happening here. I can assume from all of that that the CPU chip itself, which is really quite robust anyway, is not defective. The 6800, the Motorola 6800 is not defective. I imagine that it is working correctly. Now here on the other side of that, we have this U214, and that is a bidirectional buffer. That is, data can flow in this direction when this AB or BA is high, and data can flow in the other direction when it's low, or vice versa. I don't remember. But in any case, you should see valid data on both sides of this bus. They're calling this the D bus, the D data bus, 0 through 7, D0 through D7. This bus on the other side of that bidirectional buffer, they're calling the D prime bus. And that D prime bus goes to all the other components on the CPU board that need to be accessed to the data bus. So all 6 of the ROMs and all 4 of the RAMs, and down here the GPIB controller, as well as things that are not even on this schematic that go out to other parts of the instrument. Of course, because you have to control things besides just the ROMs and the RAMs and the GPIB board controller. All right, so when I look at the data on this D prime bus on the other side of that bidirectional buffer, I see invalid logic levels at times. In other words, it's not 0 volts and close to 5 volts for logic 0 and a logic 1. The voltage levels on these bits are somewhere in the middle, like around, say, 2 volts. And that should never happen. It should always be a 0 or a 1, or transitioning between a 0 and a 1. It should never be stuck in the middle at 2 volts. So there's something going on this side of the bidirectional data bus onto the D prime data bus. So let me show you on the scope what I see there. Something is going on this data bus. Let me show you what that is. Okay, so I'm connected to one of the data lines on the D prime data bus. And if you look over here, see, most of the time we have logic 1s or logic 0s, close to 5 volts or close to 0 volts. But right here, you can see at times there are pulses that are right around plus 2 volts, right in the middle between a logic 0 and a logic 1. That should never occur. And you can see that on all 8 bits of the D prime data bus. So something on that bus is either colliding with something, is outputting a 0 when something else is outputting a 1 and we're in the middle, or something else funny is going on. There's something on that D prime data bus that's causing invalid data. And so I need to try to determine which component that is. And quite a few things are on that data bus. Now, I had one of my viewers commented that it's very common and very typical in these 3314s that these MOSTEC ROMs, there are 6 of them in this particular instrument, can go bad and have some corrupt data in them. That will cause the exact symptom that we're seeing, that the address bus will increment through all 16 bits, just increasing one count at a time, and we never get booted up because of a defective ROM. And that's very likely the case. There are other things connected to that data bus as well, right? It could be the RAM chips that are defective, or it could be the GPIB controller because it's connected to all 8 data lines on the D prime bus as well. Or it could be something else off of this schematic on another part of this circuit. How am I going to isolate which problem, where the problem component is located? Well, I've narrowed down that it can't possibly be the RAM chips, because if one of these RAM chips was bad, each of the RAM chips are only connected to 4 bits of the data bus, either D0 through D3 or D4 through D7. None of them are connected to all 8 data bits. There are 4-bit wide RAMs. And so therefore, if one of those chips was bad, it would only affect 4 of the bits on the D prime bus. It would not affect all 8 lines of the D prime bus, which I'm seeing a problem on all 8 lines of the D prime bus. So therefore, we've eliminated the possibility that the RAM chips are bad. I have a feeling that my viewer who said that the ROM chips tend to go bad, he's probably correct, and I will have to replace all of the ROMs. In order to find that out, there's no way to find out because I cannot pull them out of the sockets. They're not on sockets. They're soldered directly onto the board. But I do have a secret weapon, and It's time to reveal what that secret weapon is right now. What's this? Another 3314? Oh my goodness. So yeah, here's my secret weapon. Here's my unit that I'm working on. I went out and purchased another 3314A to use as a parts unit. Um, I felt guilty about damaging the front panel on my original unit with the hydrogen peroxide stuff, and I promised that I would replace that front panel with the front panel from another unit. And so I had to buy a parts unit. As it turns out, they're readily available and they're really not all that expensive. So I'm going to take the front panel off of this unit and use it to repair the one that I had damaged over here. Um, as it turns out, the controller board, the A3 controller board on this parts donor unit is functioning. It's not damaged at all. So I'm simply just going to stick this controller board into my original unit and stop playing with it. Eventually, I plan to desolder the ROM chips, add sockets for those 6 chips, and download the data that's contained in them and get some EPROMs and program them with that same uh, valid data and pop them in there. And hopefully that will fix that problem. In the meantime, my donor parts unit, if we take a look at it, it doesn't have those MOSTEC prom chips. It has these EPROMs, right? See, with the little windows that are covered up with tape. Um, So these EPROMs are actually contain the program information that I need to get a permanent file downloaded so that I will have a permanent record. And then I'm going to make another set of EPROMs, program them, and pop them into my original unit, and then we'll have 2 functioning A1s. I'm assuming that it is the ROMs that are actually bad. Maybe it's not, but in any case, I do have a working A3 controller right here. So I'm simply going to take this one and stick it into my other instrument, along with swapping out the front panel, and then we will have a working 3314A. And I won't have to spend a lot of time trying to figure out what's causing that data corruption on the D prime data bus. All right, so that's what we're going to do now. Okay, so I've swapped out the controller board and I replaced the front panel that I had damaged with the one from the donor parts unit. And while I had the front panel off, I replaced the power switch that was sticking and not functioning properly. So I swapped that out as well. So now, the moment of truth. Let's turn it on and see what happens. Counting down, 3, 2, 1. Cal, 1000 hertz. I think it's working. In fact, I'm sure it's working. Um, we can we can change the frequency. We can change the amplitude. We can change to square wave, triangle wave, DC only. Very good, very good. It is repaired. All right, let's hook it up to the scope and take a look at some of the signals that come out of it. Okay, so here's the 1 kilohertz sine wave, 1 volt. We can switch it to square wave, and voila, square wave. Triangle, turn it off. Let's play with the frequency. 20 kilohertz, 110 kilohertz, 19 megahertz. Looks like it's working to me. Square wave, 19 megahertz. Oh, let's put it on 50 ohms. There we go. Well, it's got a little bit of rise time overshoot, but it's 19 megahertz, and it's a square wave, sort of. All right, triangle wave at 19 megahertz. Oh, there we go. There's 19 megahertz. Very good. I think it's working. Let's play with, let's bring it down to a reasonable frequency. Um, back to a kilohertz. All right, there's 1 kilohertz. Let's play with amplitude, sine wave. There we go. Amplitude. Zoom up. We can zoom down. All the way down to 10 microvolts. I don't know if we can see that, but it says that it's 10 microvolts. All right, I think it's working. How about DC offset? Let's try DC offset. Let's bring this up to 1 volt RMS. There's 1 volt RMS. Let's give it a DC offset. Look at that. Positive, negative, 0 volts. All right. I believe our 3314A function generator is working. But what I really wanted to demonstrate was the Easter egg, right? So let's get the Easter egg set up. I'll be right back. Okay, so I put all the covers back on the instrument and put the feet back on it and got it all cleaned up and closed up and good to go. And so the moment you've been waiting for, the Easter egg. I first learned about the Easter egg back in about 1982 when this instrument first came out. I was working at Hewlett Packard, and of course, they didn't call it the Easter egg back then. This instrument was made, at that time, it was made in Loveland, Colorado. They later moved production of this particular model to the Lake Stevens division, which is Marysville, Washington. But when it first came out, it was made in Colorado, in Loveland, Colorado. And the guys out in Colorado told us about the Easter egg. Of course, they didn't call it an Easter egg back in those days. Um, the IBM PC had just come out recently, and it was still running on MS-DOS. We hadn't even developed Windows yet. In fact, I didn't have an IBM PC. I had a Commodore 64 at home. That's what I was using back then. Um, but they called it, instead of calling it the Easter egg, they didn't use that terminology back then. They just called it the undocumented um, arbitrary waveform demonstration. That's what it's called. And what it really is, of course, is Handel's Messiah. So the Hallelujah chorus from the Handel's Messiah. That's what it is, and it's programmed in there as an arbitrary waveform. And there's a special way you get to it. Let me show you the setup first. I have it connected from the output through a T, and one side of the T goes into my analog scope. All right. The other side of the T goes through a step attenuator because it was actually playing too loud, and a 50 ohm termination. And it connects to my guitar amplifier over here. All right. So the way you activate the Easter egg is by, let me get my camera set up. All right, let's get the camera set up so that it shows both the screen and the scope. I don't even know if I can do that. And there we go. Let's try that. That should work. That should work. Okay. So what you do is you hold the blue button and then 2 other buttons at the same time, and then you turn on the power switch. and then it will activate that hidden Easter egg. All right, so here we go. Let's do it. No, just kidding. Um, now we'll do it for real this time. I'm not going to play around anymore. Here is Handel's Messiah as played by the Hewlett Packard 3314A function generator.